Alright, so what we're going to talk today is about section 16.8 through 16.10 in the book. 16.8 talks about benzyne. So this is benzyne over here. It's an alkyne inside a benzene ring. This is really, as you might imagine, a really strained alkyne. It can form in the context of certain reactions. It is much too reactive to be isolated, but it certainly can form. So the first question is, how do we know it can form? Well, if I start with this bromobenzene here, and I label that carbon here, so that if I make this carbon now, we'll zoom in a little bit, if I make this carbon to be radioactive, and I treat that now with a strong nucleophile, in this case the amide, the NH2 minus anion, what I would expect to get is a regular nucleophilic aromatic substitution reaction, alright? So then where the NH2 would come in here, we would form a Mesenheimer intermediate, and that would give us the, then collapse back to give the aromatic compound and this desired product. What I get instead is a one-to-one mixture of the compound with the nitrogen on this group and the nitrogen over here at this carbon, okay? So the NH2 is substituting at the carbon you would expect, but it's also equally substituting at the carbon adjacent to the one that had the bromine. And the way to explain that is via the formation of this benzyne intermediate. So what this NH2 group is going to do first is pull off the H that's on the adjacent carbon, alright? So if I pull off the H, then kick off the bromide, I form benzyne. I'm going to go through the mechanism of benzyne formation in a second. And then that benzyne is what reacts with the NH2 minus to generate this mixture of products. So again, how do I form benzyne? If I have a strong base, I can pull off the proton adjacent to a leaving group, swing the electrons into the double bond to form a triple bond, and then kick off the chloride. So I go from here, pull off the proton, triple bond, kick off leaving group. I now form this benzyne intermediate. If I react that with water, in this case, I'm going to generate phenol, the alcohol over here. That's a way of trapping this high energy, very fleeting benzyne intermediate. Benzyne also actually works as an excellent dienophile. Alright, so if I have a variety of dienes, I can trap the benzyne to generate new 6-membered rings in the Diels-Alder reaction. So again, if I'm looking over here at a molecule like this guy, this will be my diene. It can react with a benzyne dienophile, and that's a very great reaction to undergo. It's pretty important. Okay, and that's pretty much as far as benzyne is. It forms in the context of extra strong bases that are able to pull off this proton adjacent to halide leaving group. So you need the halide leaving group, and you need the strong base, and then you can, so OH minus and H2 minus are pretty much the only two examples that we're going to talk about in this case. But you pull off that H, you generate benzyne. It can then react with the nucleophile, the NH2 or the OH. It can also react with Diels-Alder dienes to undergo a Diels-Alder reaction. We can do also, so that's benzyne. The next thing I want to talk about is section 16.9 in the book, which is the oxidation and bromination of substituents on the benzene ring. So until now we've been talking about how to introduce things onto the benzene ring, just putting substituents on, but they're also, once they're attached to the aromatic ring system, there are a number of other reactions that they can undergo, and this can be potentially very useful in the context of running synthesis, designing syntheses, especially of the multi-substituted, polysubstituted benzene ring. So the first reaction I want to talk about for this is oxidation of the side chains. Pretty much if I have any alkyl group attached to the benzene ring, so that's what this R is, if I react it with KMnO4, potassium permanganate, what I generate from that is the corresponding carboxylic acid. The mechanism for this is very complicated. However, what it does involve is radicals, and the only caveat is that what you need the alkyl group to have is to have benzylic hydrogen, so you can end up forming the benzylic radical. So, for example, this terbutylbenzene here is not going to react with KMnO4 because it has no radicals attached to it. If I put either of these H's on here, now this is going to react to form the carboxylic acid. And I just want to be clear about this. Regardless of how long the side chain is, you always form just the benzoic acid, okay? KMnO4 always forms benzoic acid. Okay, so I can have a 1 carbon side chain that forms benzoic acid. I can have a 21 carbon side chain that also forms benzoic acid. You effectively kick off the rest of the side chain to generate the desired product. Alright, that's oxidation. We can also do radical bromination if you use M-bromosuccinimide. That's this compound here. This is M-bromosuccinimide. You are responsible for knowing that nomenclature. And I react it with a substituted benzene that has benzylic hydrogens. I can substitute one of them for a bromine. So again, I take off one of these H's, I replace it with the bromine. The mechanism you can go through in your book, it's a radical chain reaction. I can generate a benzylic radical and then combine that with the bromine radical to form that product. Those bromine radicals are formed from Br2 breaking. I generate Br2 from N-bromosuccinimide, and HBr forms Br2, which then breaks up into bromine radicals. Alright, so you can go through your book and figure out what that radical chain reaction is, but it's certainly useful to note that once you put a functional group, an alkyl group with benzylic protons onto a benzene ring, that proximity to the benzene ring makes them able to pull off a proton and form the radical, and then do a add the bromine radical there as well. There's one other class of compounds and reactions that I want to talk about, and this is section 16.10 in your book, which is the reduction of the aromatic compounds. So if I have a compound like this, and I want to selectively reduce either the alkene or the carbonyl, I can do that. So I can selectively reduce the alkene, using hydrogen, palladium, in ethanol. If that alkene is close to the aromatic ring, so if the alkene is conjugated with the aromatic ring, so that's pretty useful. If I want to reduce that aromatic ring entirely to cyclohexane, I can do that using hydrogen with platinum or hydrogen with rhodium. I can reduce the entire system using hydrogen with a platinum or hydrogen with a rhodium on carbon kind of catalyst system. But again, being able to selectively reduce this alkene while leaving the benzene ring intact and leaving the carbonyl group intact is a pretty useful situation here. What I can also do now, if I want to reduce I can reduce carbonyls that are directly attached to the benzene ring. So again, this is only related to if I have the functional groups directly attached to the benzene ring. So here, if I put this molecule like that, and I ask, how can I reduce this carbonyl? Well, I can do that with hydrogen on palladium as well. And again, that selectivity is related to what's directly attached to the aromatic ring. So in this case, when the alkene is conjugated to the aromatic ring, I can reduce that with hydrogen and palladium. And in this case now, where the carbonyl group is attached to the aromatic ring, I can do that with hydrogen and palladium as well. The final thing to note about reductions is if I have a nitro group attached to the aromatic ring and I treat it with hydrogen and palladium, that reduces the nitro group as well. So in this particular case, what I would get if I treat this compound with hydrogen on palladium is an NH2 group over here. That's from the H2 palladium reducing down the nitro to a amino group, and then I would get rid of that acyl group and form the corresponding ethylbenzene substituent. So that's pretty much what is covered in 16.2 in the book. I know I went through that a little bit quickly, but you can go through this. Hopefully you can rewatch this lecture as necessary, just to make sure it's clear to you guys. And then really, like we discussed in the problem solving session on Wednesday, March 4th, use that functional group tunability to help us with our molecule. What I mean by that is I can keep the acyl group on, make that guy do meta-directing, and then when I'm done using that directing group's influence, reduce it down to ethyl, and then get my desired product that way. The final section in chapter 16 in your book is the polysubstituted benzene, and that's something that we talked about again in the problem solving session, how we can rationally design the synthesis of these polysubstituted benzenes by looking at their direct and group capabilities, sort of putting everything together. For the midterm, you are responsible for all of the material through chapter 16. You are not going to be responsible for what is covered in chapter 17.